Hello, today we are looking at momentum. We're going to kind of review through everything, and that will help us get ready for the AP test. This isn't meant to be sort of a complete set of notes for how to do momentum. This is sort of, you kind of have the basics, and it's a little bit of review, a little bit of how can I make sure I know how to approach different problems. So, first of all, let's go ahead and just look at what are the basics. Remember, for momentum problems, you know something is a momentum problem if there is a collision. So you have two objects hitting each other, bouncing off in some way, right? So colliding, bouncing off, something along those lines. And then it's asking for velocity. Now, the reason you know you can't use energy in this situation is because they're asking for velocity, so that's usually a clue for energy. But because we have to have two objects bumping into each other, maybe pushing off of each other, but they're actually directly touching each other in some way, it has to be a momentum question, not an energy question. So anytime they're touching, energy isn't going to be conserved, pretty much. We'll get to that exception in a little bit. So that's sort of how you know if something is a momentum question. Now, how do you set up momentum questions? So first step is you're just going to write something like the sum of the initial momentum is equal to the sum of the final momentum. Sometimes I'll also write it as Pi equals Pf. And this is an important step because oftentimes on the AP test you're given points just for using conservation of momentum. So by writing that at the beginning, you prove that you are using conservation of momentum and they can give you that point. You want to be careful not to just jump too far into your work so that someone might misinterpret what you're doing, especially if you've made some mistakes there. So that's step one. Then step two, plug in momentums. So if we had something like block 1 is moving at, let's say, 1 meter per second, and then is going to collide with block 2 that initially is moving at 0 meters per second, and then we're going to have block 1, it's going to stop, and block 2 is now moving at some velocity of question mark. Right, so we're going to plug in our momentums. So I have something like Pi equals Pf. Then I only have one object moving at the beginning, so I have mv1 equals mvf2. Remember, everything on the left-hand side is initial momentum, and everything on the right-hand side is final momentum. So sometimes the variables may be used more than once. If that is maybe a little confusing, you can always do like M1, V1I, and kind of differentiate between each different variable, but that's not necessary. You can just kind of follow down here. And then you go ahead and solve with units. Units is very important. Sometimes you will lose a point if you do not include those units, so it's really important that you do include your units. Then you're going to go ahead and just plug and solve. So here we would just say m, let's say both m's equal 1 kg. Okay, so everything is m equal 1 kg. So I have something like 1 times 1 equals 1 times vf2. And so I have 1 equals vf2. And so my final velocity is equal to 1 meter per second. And then because I have this drawing, I can also add to the right. Anytime there's a direction involved, it would be good to write it. If you're unsure of the direction for some reason, then you maybe don't write it. But remember, if we got a negative sign here, that would be an indication of direction. Okay, that negative would indicate the opposite direction. So it is really important in a momentum question that if you have objects moving in opposite directions, that one of them needs to be negative. This sort of goes back to our kinematics stuff, where we need to set one side as positive and one side as negative. Obviously that would be a little bit backwards of what most people would do, so sort of this would be our standard, and that's fine. Sometimes the problem might give you a positive and negative, so that's definitely something to watch out for, but you can set that positive and negative, and then negative here would mean to the left, positive would mean to the right. That's sort of just our basic. Now remember, there are different types of momentum collisions. Can you think of the two main types? Yeah, so we have perfectly elastic And then we have perfectly inelastic. Okay, and sometimes we think of this as just those are the two types, there's nothing else, but what I want you to think of that as these are two opposite ends of the extreme, okay? And so that most collisions happen somewhere in the middle part here. So these are where most collisions are, and they aren't either type, okay? So most collisions aren't necessarily one of the other special types, but then at the very ends of the spectrums we have the perfectly elastic and perfectly inelastic. So perfectly elastic, I remember by saying E, that goes with energy. So energy is conserved. Specifically, Ke. Okay, so kinetic energy will be conserved. So in this case, I can always set up my Pi equals Pf, but now I can also do an Ei equals Ef, and it ends up something like Ke1 plus maybe Ke2 equals Ke F1 plus Ke F2. Okay, and so then I can also set up these kinetic energies as well as my momentums. Now, anytime you have two objects colliding, there isn't sort of friction over a long period of time, it's a very short period of time, you can always use Pi equals Pf, or maybe better yet, write it as the sum of Pi equals the sum of Pf. So that's always valid. But in the special case of elastic, you can also use this. Now, I would suggest if this came up on an FRQ question, it's going to be a lot of work to solve. So what I would do is I would set everything up, plug in numbers, stop, and then come back to it at the end. This is not one to spend not an hour, but a long period of time, even 5 minutes, just doing this algebra that might only be worth 1 point. So if you come across an elastic problem on the AP test, that's fine. Just set it up, get your KEs and your momentum set up, plug in values, and then go ahead and move on. Okay, then on the opposite side of the spectrum, we have perfectly inelastic. So this is where one object sticks to another object. Okay, and so the way I think of it is I maybe have a block, and then I have this bullet heading towards this block, and then the bullet ends up sort of inside the block. So we have this bullet inside the block. And so I think, okay, well that's inside the block, and that's inelastic. So inside. And so that's the way I remember it. And then the tricky thing with this is to remember that if one object is inside the other object, both final velocities, so the bullet final velocity, has to be equal to the final velocity of the block, right? Because now they're one big object. And so the way we write this, sort of mathematically, if we're going the sum of Pi equals the sum of Pf, we'll have something like MVI plus MVI. So these are, MVI plus MVI. And so those would be our two objects. Maybe this is the block and this is the bullet. Remember, if the block was not moving, you wouldn't need to write it, but in this case, we've just written it to show you. And then this is going to equal only one momentum. So I'll have just M block plus M bullet VF. Okay? And so this is kind of how it sets up. Now this formula isn't on your formula sheet. If you remember that this is true, you can figure out this formula because all you're doing is factoring out this VF here. And that's not too complicated, but this is definitely something that you want to be familiar with so that if you encounter an inelastic question, you can remember that you're going to add those two masses together because you kind of have only one big object at the end because they're now stuck together. They're moving at the same speed. So those are the two main types. Remember, most collisions are somewhere in the middle, so you don't need to feel like, okay, is it either elastic or inelastic? You can assume that it's neither unless the problem gives you some specific clue. So for example, if it says they stick together or it says energy is conserved, that would be your clue. Now, remember, momentum is conserved in both x and y. So what that means is, if you have a collision where it's not just a head-on collision and then they're just sort of moving in this one-dimensional axis, where I have just plus minus, you could also have a collision where maybe something like this, and so it's not quite head-on, this one will go here, and then this ball will end up going in this direction, right? That's a somewhat intuitive thing. Just think about pool. If you kind of hit something off-center, then this upper ball will go up that way, and this lower ball will come off this way. And so you can kind of use that to predict what's going to happen. But the way you would set this up is actually using an XY chart. And so you would set up a sum of momentum in the y direction, x direction equals the sum of momentum, final momentum, and then the same thing over here. Now in this case, because the initial velocity is only in the x direction, my initial y momentum would just be 0. And so then I would go ahead and solve from there. And then once you found these velocities, you'd have a velocity here and a velocity here. And to find the sum, you'd use that Pythagorean theorem. Vy, Vx. So then something have like V total equals root Vx squared plus Vy squared. Just sort of Pythagorean theorem, knowing how to find that hypotenuse. So not too tricky, but definitely a lot of algebra. Once again, this would be a spot to set this up. Go ahead and plug in something like 0 equals mvf plus mvf. Plug in numbers here for all these things that you know, and then stop and come back to it at the end if you have some more time to work on stuff. So that's just how you'd set up a two-dimensional thing. Not any harder, but you just have to do it twice. So just like kinematics, if you had two-dimensional kinematics, you got your x and your y. Same thing here. You got your x and y. So not too difficult, but definitely something just to highlight on as a possibility of a question. Remember, we do have some other formulas that are a little bit unrelated. So on the formula sheet, they only give you 3 formulas for momentum. So they just have P equals mv. And remember, these little arrows here at the top, those indicate that those are vectors. Okay, so momentum is a vector, velocity is a vector, mass is not a vector. Mass does not have a direction. But that does kind of indicate that they are at least somewhat expecting a direction if they are asking for a momentum or a velocity. Now, if they only ask for the magnitude, or they ask for the magnitude of a momentum or the magnitude of a velocity, then you don't need to worry about the direction. Remember, the magnitude is just the number. You don't need to worry about that direction. Now, there's 2 more formulas. We have F equals dp dt, and they also signify that F is a vector here. And then also J equals the integral of F dt equals root, or change in P. Okay, so this one right here, it looks a little bit complicated, but it's actually not too bad. So the way I think about this is F is just m times a, and so this is also just m dv dt, right? And if you look at that, a is just dv dt. That's something we already know. So we just multiply a equals dv dt by m, and we get F equals dp dt. So just kind of including that that mass in there gives us momentum and force instead of just acceleration and velocity. And then J here is impulse. Remember, that is the force times the time. If your force is constant with time, then you can just do force times time. You don't need that integral. But if force is a function of time, then you are going to need to use this integral. Now, this would be your start of collision, and then the top one would be end of collision. Now, this would only be when those 2 objects are touching. So, for example, if you're looking at like the impulse of someone hitting a baseball, it's only when the bat is in contact with the ball. So it's going to be a very short amount of time. And then obviously this is equal to the change in momentum, which would just be something like mvf minus vi. So once again, not necessarily too difficult, but it could be a little tricky depending on whether or not you've kind of remembered to look at it before. One other thing to think about is the center of mass. Now, The formula for the center of mass, this is sort of the one last formula that we have, kind of related to momentum, is not too bad. So it says xcm equals the sum of mi xi over sum of mi. Now, a better way to write this maybe is something like m1 x1 plus m2 x2 plus all over m1 plus m2. And so this finds the center of mass. Remember, if you have the center of mass of two strange objects, you can still find this sum by using this formula. So you'd use the center of mass. Now, the same thing works in the y direction or even the z direction if you had that for some reason. So you could also find sort of a two-dimensional center of mass with different point masses here maybe, and then this. Remember, if I had something like a bar, if I have the center of mass of that bar, I can treat that bar as a point mass where all the mass is coming from that center of mass. So even if something isn't a point mass, I can treat it as a point mass if I can find out where the center of mass of that object is. So for example, the center of mass of a sphere would just be that middle of the sphere, right, if it was uniformly distributed. The real power in center of mass is knowing that the center of mass can't change without an external force. Okay, unless it's already moving for some reason, it's not going to change without an external force. And why that's helpful is if you have some sort of scenario where it's like maybe you have a person on a raft and this person is moving over here. As he walks, he's going to exert a force on the raft, but it won't be an external force. And so the types of questions where it's really helpful is to say, okay, this person's here, where's the midpoint of this raft going to be after you move? And so you say, okay, well, the center of mass is here initially. When he is over here, the center of mass is now going to be over here. So this spot here needs to shift over to this spot, okay, because that center of mass needs to be in the same spot. You can also use, instead of just center of mass, you can also use center of velocity. And so this looks exactly the same, except for the only thing I'm changing is these x to v's. You just go ahead and change this to a v. And once again, the center of velocity cannot change without an external force. So this would be sort of, maybe you have two objects and they're colliding, and I know something about the center of velocity is moving in this direction. The center of velocity will keep moving in this direction unless there's that external force. So that can be another helpful tool to analyze what's happening. In theory, anything that you can solve using momentum, just regular old momentum, you can also solve using center of mass. But that just gives you one more tool in your toolkit to potentially approach a problem that's maybe a little bit trickier. That was momentum for the AP Physics C test. Hopefully you were able to learn something. Here are some videos about more in-depth, more notes. So if you were really lost, you didn't really follow along, you can get some more notes here. And then here are some review questions. So if you feel like you kind of got it and you just need some more review questions, that would help you there. Okay? Have a great day.